Hey y'all, so for the second class, somehow I said I was going to do number 4 in our group, and I never did. So my apologies, I just forgot about it. And then I got a note from the math lab that somebody was asking for help about it, and I'm so glad you followed through on that, because I certainly didn't. Here's the premise. It's asking you for g prime, and g itself is an integral. It's actually kind of a big part of fundamental theorem of calculus, but here's kind of the long and short of it, and you'll be able to do this really successfully. It's pretty simple to work with. So what happens if you have g and you want g prime, you take the derivative, and you always have to do it to both sides. So if you noted here, I'm just going to take the derivative of both sides, and so I get g prime on the left, and then the derivative of the integral on the right. This is where the magic kind of happens. You can actually cancel the integral with that derivative because they are inverses, and that's part of the fundamental theorem, is that derivatives and inverses are inverse operation. Derivatives and integrals are inverse operations, so they cancel. What happens though is in the process of integration, though, we do sub in the x cubed and the 0 into the antiderivative, and since that's part of an integral, when we're taking the derivative and canceling the integral, it doesn't take away from the fact that we are subbing in that upper and lower bound. So that means when I'm taking the derivative of this thing, I actually have to think of it as a chain rule, because I've subbed in this x cubed into the arcsine of t. I mean, this is kind of a wild function, the inverse sine function, arcsine function. You want to put that upper bound x cubed into it, but when you're taking the derivative of arcsine of x cubed, you have to take the derivative of the x cubed on the outside. That 3x squared is the derivative of the inside. Now you might be wondering, why didn't I take the derivative of arcsine? Well, I did, but remember I'm taking the derivative of the integral of arcsine, so it canceled and just left arcsine. But that x cubed inside there, I did have to take the derivative of that on the outside. That's part of the chain rule. So the derivative of the outside was canceling the integral. The derivative of the inside is the 3x squared right outside. But don't forget to have the x cubed inside there. Same thing for the 0. The only thing is when you sub in 0 to arcsine, you actually get a number. And so the arcsine of 0 is actually, 0 degrees would be one solution. But the derivative of a constant is 0. Hey, don't you have a plus c with antiderivatives too? Well, yeah, but the derivative of a c, and by the way, it's a definite integral with that 0 and x cubed, but whether you put it or not, the derivative of the plus c would be 0 as well. So in the end, there is a shortcut to this. Basically, you end up putting in derivative, and there's that piece of it. The two parts that are 0 I've just eliminated. And so here's the general rule. If you are going to take the derivative of some integral, and there's a function in the upper bound, and there's a constant at the lower bound, you're going to end up getting the upper bound subbed into whatever you're integrating. Remember, the derivative cancels the integral, so you're left with just g. The upper bound f of x goes into g, and then right outside of it is f prime of x. That's it. That's the shortcut. Now if you go back and apply that to the one we just did, it basically means if you're taking the derivative of an integral, put the upper bound in, take the derivative of the upper bound right outside of it, done. And so that's one of the fundamental theorems. It's kind of a real specific case of the chain rule. So hope that gets you through there. The first class got this. I'll send it to all of you. Second class, we missed that altogether. So here it is.